Okay. J Arnold is a tutor and homeschool teacher, born and raised in the Jacksonville area, homeschooled from 7th grade through graduation. Jay fell in love with math and science, and his dream was to become a mad scientist. While earning his degree in chemistry from the University of North Florida, he discovered a passion for teaching and a knack for making the complex understandable. Since 2002, Jay has helped many local homeschool groups, yes he has, and thousands of students, public, private, and homeschooled, develop an understanding and even a love for the mysteries of science and math. Jay has been married to his lovely wife, Sheri. I lost her. There she is. Lovely wife, Sheri, since 2005, and they have created 3 beautiful and exciting experiments that they call their children, ages 12, 10, and 7. He also has a deep love for Star Wars and pizza, often together. So if you guys could please clap for J Arnold.
Well, thank you for that introduction, guys. I'm going to try and speak loud enough that you can hear me in the back row. If not, I'm happy to use the microphone. But thank you all for joining us tonight. I'm actually really surprised that this many people came out for a math seminar. Honestly, how many of you were dragged here? Let's see it. I know some of you were.
Oh!
Including my kids have their hands up.
Look at that.
So that's okay.
Oh, look at right here.
That's okay. That's okay, guys. Hopefully we'll make it interesting enough that you won't fall asleep. If you do fall asleep, there may be a quiz at the end that you'll have to come up and answer questions live. So just be careful with that. So thank you, Ashley, for that introduction. My name is J Arnold. It is just the letter J. You know, I noticed all these other people speaking this week that have letters in front of their names and just had to kind of fit in there. Anyway, no, I'm blessed to be joined by my family tonight, my parents who surprised me, former babysitter and family friend, former students of mine. So it's just very exciting to be able to talk to such a broad group of people, and I hope to get to meet some of you guys tonight after the session. So let's get started. You are probably all wondering the same question when Ashley asked me to start with Fibonacci numbers, when she said Jacksonville Science Symposium. Well, wait a second, I thought we were talking about science, but there's a lot of good reasons why we're going to start with the math. And actually, I'd just like to kind of mix it up a little bit, let you guys interject. Before I put any of my bullet points up, maybe you have some that I've already put up, or some that I've already written down, or maybe you have some that I didn't think of. But why do you think Ashley and the powers that be decided to start this week with a math seminar? Any ideas why? Do you think math has a place with science? That was kind of some of the questions she was asking. I would agree with that, but there's probably a pretty good reason why we start with math. No takers? One in the back maybe? Yes, sir? Math is absolute. By that you mean? Repeatable, provable. It doesn't change, okay? And that is something I have on the screen. That's really important. Any other takers? Reasons why math is vital for a science symposium?
Order.
Order, okay? There's lots of order in math. Even if you don't like math, as some of my students might attest, even the one that quoted 18 digits of pi tonight. Yeah, it follows rules. It's something that we know how it works. So let me just start with this. It's a language. Math is a language, and you think, well, how is that? Because it's just numbers, and if you get into algebra, then you got letters. But it is a language, because if you think about a language, what do languages have in common? Whether you speak French, or Klingon, or English, what is the common factors of a language? Well, first thing is that it has letters, okay? Now, when we say letters, yes, in algebra, we use real letters, but numbers are letters also. They represent an idea. In a verbal language, they represent a sound, and this is a rule that they follow. This is what they represent. It's an idea. And in mathematics, we have letters, which can also be numbers. There's also words. And maybe this is beyond your math skills. Maybe you forgot it from 40 years ago. But 4x squared is a word. It's something we call, anybody know from algebra? Starts with a T, ends with erm. Hey, somebody said it, it's a term, okay? Those are our words that we put together, and when we have words in our language, or whatever language you know, you put those together, you make a what? You make a sentence. So we have sentences in math, and you're familiar with those. There's some letters, there's some words, and we have a statement. And just like in language, just like in any sentence that you state, it's either true, or it's false, or maybe it's neither because it's an opinion. But with math, we don't have opinions. We just have, as he said in the back, absolute statements that are either true or false. They might be conditional. We won't get into that tonight. All right. There are also rules of how you're allowed to put words together, sentences that have to work this way or not. And this is just one example of commutative property. This is a rule that says you can have 2 plus 5 equals 7, or 7 plus 5 equals 2. It works the same. It works with multiplication as well, but it does not work for subtraction and division. And so those are just reasons why I say, and I'm pretty sure that you would agree, math is a language. So why do we need that then? Well, there's some properties about this language. It's universal. When I say universal, I mean what about languages? Love is a universal language, right? Chocolate is a universal language. Some of you would say
Morse is a universal
coffee.
language.
What was that?
Morse code.
Morse code. Yes, okay. So when we talk about math being universal language, everybody knows it to some extent or another. Even as a child, you learn some basic mathematics, and it's something that you can interact with somebody that does not speak your verbal language, and you can explain the same information with mathematics. It's an ancient language. It's been known since ancient Greece, Rome, Babylon, Egypt. They all had mastery of mathematics, and it's one of the common threads of humanity. Any history class you've taken, whether it's from a biblical point of view, whether it's from a humanistic standpoint, or evolutionary standpoint, mathematics can be traced all the way back to the dawn of civilization. And it carries these ideas that allows us to continue our understanding. And thankfully it is absolute because those ideas don't change as time has gone on. It's an inherent language. What I mean by that is arithmetic, sequences, measurement, all these things that were developed by these aforementioned cultures, they are so basic. You learn how to count because you know I've got this many toys, or I've got this many blocks, or I've got this many sticks and stones or sheep, whatever it is. Those are things that you know we have to quantify them, we have to learn how to add them and subtract them. The bartering system, all economic systems are built off of some form of mathematics. And so it comes with the dawn of civilization. And it's an immutable language. That's a big word. Does anybody know immutable?
Mutable?
Immutable. Immutable.
Unchanging.
Unchanging, okay? Again, coming back to the first point was mentioned tonight, it's an absolute language. It's not something that is invented. If you don't hear anything else I say tonight, this is my biggest point that I introduce my students to in my mathematics class. We discover mathematics. We don't invent it. We might put letters on it that make this rule. You want to call it the Pythagorean theorem, you want to call it Fibonacci numbers, whatever you want to call it. But those rules exist already. And so that's what we mean when we say it's an immutable, it doesn't change, it was already there, we just discover or develop those rules. And then finally, it's the language of science, and that's why we're here tonight. Because science is how we quantify the world around us, how we measure it, how we understand the world. If you don't have a language to communicate that, you can't communicate that information to other people. Thankfully, with this language being preserved, with this information being preserved through mathematics, it can be preserved for generations to come. And so with that, we are going to move on to the title of tonight's session. And I just want to remind you, it's on Fibonacci numbers. We'll talk about those. Sequence patterns, we'll talk about that, and nature. So let's start with Fibonacci. Who is he? Anybody familiar? You've heard? Maybe I should ask this. Who's never heard of Fibonacci before you signed up for this seminar? Only one person. Wow. Three people. 4 or 5. A little better. Okay. So the bar is pretty high for me. For those of you who are familiar with it, maybe you've heard it, but you don't really remember what that means. Fibonacci was an Italian merchant from the 13th century, 12th and 13th centuries, born probably in Pisa, okay? Leaning Tower, think about that. His father was a merchant that was able to afford him an education by Arab mathematicians. His name really, Leonardo Pisano, from the land of Pisa, from the city of Pisa, probably got his name from Fibonacci, Filius, son of Bonacci, his father Bonacci. One of the things I looked up, one of the last things I looked up about Fibonacci is that the name means lucky son. So maybe he took that as a double entendre there. He was a genius, to put it simply. The man was educated by Hindu and Arabic mathematicians, and he took some of those ideas and wrote a book called Liber Abazi. It's the book of the abacus. He took those ideas, put them all in one place. He even admitted that his ideas were not unique. Anything that I say tonight, I got from somewhere on the internet. It's not unique ideas. I'm just putting it in one place for you. That's what he did for the Western world. And in his book, he gave us information that led to discovery of decimal system in the Western world. We were not using that at the time. Proportions, there was geometry, and something that the Arabians called al-jabr, which we call algebra. We have the Arab and Hindu community to thank for that. His ideas led to an invite before the Holy Roman Emperor Frederick II, and this led to a years-long professional relationship between him and the scholars that were commissioned by the emperor to understand the world of mathematics and how that relates to controlling of the empire and mastering the world around them. So that's a little bit about the guy we're talking about. Here's the famous sequence, okay? He proposed this in his book, and his story comes from a word problem regarding rabbits. A certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that pair in a year if it is supposed that every month each pair begets a new pair, which from the second month on becomes productive? Each pair of rabbits produces a male and then a female. They're alternating. Nobody gets sick and dies. Nobody has twins. Very strict rules for this thought experiment, but this was his experiment. Again, this idea was not something unique to him, but he put it down in words for the Western world, and it led to the first recursive sequence known in Europe. A recursive sequence is it's a formula where you use the last answer to build to the next one. And here it goes. 0, 1, 1, 2, 3, 5, 8, 13. What's the next number?
21.
21. Oh, you guys are quick, okay? So what's the pattern here? You start with 0. Some lists will not start with 0, okay? And we'll see why that is in a little bit. But you take this number and you add, the next number would be 1. You have to have something here. You can't just do 0 plus 0 plus 0 plus 0. That's kind of a boring sequence. So we'll do 0 plus 1 gives us 1. And 1 plus 1 gives us 2. 1 plus 2 gives us 3. Plus 2 is 5. Plus 3 is 8. Plus 5. There you go. On and so forth. So this is what we mean by a recursive sequence. You have to have the number before to figure out what the next number is going to be. And again, this was not an invented sequence. He is not the first person to have even proposed this idea, but he realized its relationship to what he had discovered from the Arab and Hindu mathematicians and put it together. He's the one that gets the credit for it, even though it wasn't called the Fibonacci sequence until the 1800s. Here's the form, if you can understand this fancy notation here. If you take the second number after in sequence, it's really going to be the prior number in the sequence plus the one before that. So if we take 8, we're going to start with 3, which is our first number. Add 2 to that. Add 2, it's 2 terms that you're adding. So you're going to add the 3 plus the 5, you get the 8. That's just the formal way of having it right there. Well, let's talk about these rabbits a little bit. It looks like this. You have your pair of rabbits, and in the second month, they're able to produce one set of offspring. That in their second month is able to produce one set of offspring. That in their second month is able to produce one set of offspring. But these rabbits here in the middle aren't done reproducing, because now every month after that, they're able to reproduce once again and produce a pair and a pair and a pair. And each one of those pairs are able to reproduce a pair. And so as we go across the calendar here, January you start with one pair, and then they're not able to reproduce until the second month, but it takes a month for them to become fertile. So one pair in the second month, and then 2, and then 3, and then 5, and there's your pattern right there. This is just one example. We're going to see probably about 20 examples where the Fibonacci sequence shows up. Again, this problem is specifically contrived to work with the Fibonacci sequence. And we're going to see some places where it works and some places it doesn't. I was looking for a place to work in this meme, and this was the best place. The first 20 numbers of your Fibonacci sequence here, 0, and then can you see I did 1, 1, 2. Actually, I have nothing up here. That's my first one, right? So 0, 0, 1, 2 entries, 3, 5, and then 8 entries, so on and so forth. So we are going to use this list in a little bit to give you a trick. Anybody familiar with this meme? This is one of my favorite memes, but that's okay.
Explain the meme.
All right. This guy's a rapper. His name is Exhibit with an X. I'm not really sure what they did to, anger the meme gods, but they just take this, yo dog, I heard you like X, so I took X and with your X, so you can do Y with your Y, whatever it is. I passed a pickup truck one day that had a Power Wheels truck in the back of it. That would be a perfect situation for this meme. Yo dog, I heard you like trucks, so I put a truck in your truck so you can drive while you drive. Something like that. So I put the Fibonacci sequence in a Fibonacci sequence. There you go. It's recursive, right? There we go. All right, well, let's talk about Fibonacci sequences in nature. And there are going to be some confirmations of things that maybe you heard about Fibonacci. Maybe some bubbles popped, some myths dispelled. Let's look at where this plays in nature. First one we want to talk about leaves on trees. Actually, I'm just going to give you all of these back to back. I have them all on one slide and we'll break them down. So we'll look at petals on flowers, genealogy of male beasts. These are just 3 examples that I'll give you some pictures for and show you how it works. So leaves on trees. Here we have elm, cherry, and pear tree. First of all, let's count how many leaves we've got. We've got 3 leaves in this set, and it takes 1 full turn to get to 3 leaves. 1 and 3. Yeah, those are Fibonacci numbers. You start here at leaf 0, 1, 2, 3, 4, leaf 5. 2 turns, 2 full turns until what they're really saying is that this leaf that was pointed straight out of the screen towards you, it takes 2 full turns and 5 full leaves to get to a leaf pointing directly back at your face. The pear tree has a 3-turn cycle.